So this is a similar problem on homework 8, gain bandwidth, which is really the fact that op-amps right, have a transfer function, right? Before, like H of S in EE98, right, equaled, or it went towards infinity, right? So there's no frequency response to it, it's just infinity. But now we have various transfer functions that look an awful lot like low-pass filters. And these capacitances come about because transistors have diodes which are built out of materials that are inherently form capacitors. And so we end up putting bigger capacitors in here to mitigate some things. All right. So here we have a transfer function, and we can see that there's a pole at -10 and at 100K. Hey, Nick, that's a great question. But I guess I'm just going to put in quotations, real. Okay. That gets into the nature of reality, where even a resistor, if you use Maxwell's equations, right, has a capacitance and an inductance, right? Except that certain frequencies, it appears that there's no frequency dependence. Capacitance is the same. And so in fact, there's, you know, even in a simple op-amp, there's over 20 capacitors, right? So what I'm doing is modeling the biggest or the most important ones. So to me, more realistic, okay? But whenever I'm designing, I start actually here, right, in 98, making those assumptions. And then as I progress or run into issues, I make a more accurate model as I go along. And the thing about, let's say, EE98, 97, those experiments are designed so that you never run into this. Okay, that's everybody does that. Okay, it's not just we're trying to keep things from you. All right, so we have an op-amp. We have two real poles, right? And so actually the op-amp itself is, right, overdamped, right? And you might not have seen it in this format in 98, but that's okay. You'll recognize the structure of it. Okay, so if I just had a transfer function, right, I need to find the poles of this. In 98, you might have looked at just the roots, but you would have called it roots, but the way you solved an RLC circuit is you would have come up with some function like this, and you would have set it equal to 0, right? Where there's things that you can do to, you don't really have to derive the whole transfer function to get this denominator. But that's really what was going on, right? And if I set that equal to 0, right, I get plus or minus R divided by L squared minus 4, A is 1, divided by LC, right? And if this was bigger than this, then you got plus or minus 2 real numbers. And so that means you get 2 different poles. If this were equal to this, you'd have +0, -0, and you end up having two repeated poles, right? They're the same. And then if this term is greater than that term, you get plus or minus some real number, plus or minus a complex number, right? And so the pole in this case would be minus R over L plus or minus okay. So this idea of over, under, and critically damped, right? You would have seen it before. If you're like me, you probably forgot it, right? Until you look at it again. But that's where it's coming from, all right? So now, rather than an RLC circuit, we have a transfer function that these poles are due to capacitances, not inductors, all right? And with no negative feedback, they're going to be real, right? This is HS of the op-amp, not this whole thing. So, but when we put this feedback right here, we change H of S, and we can actually either stay overdamped, it can become underdamped, or it can go to critically damped. All right. So I'm just going to continue to write over here, just in case some of you are still trying to capture that. So let's go to our op-amp model signal flow graph, right? And I'm just going to put 100. Now in my notes, right, I use 1 meg, even though an SI, it should be 1 capital M. That's just because I use LTSpice a lot. Okay. The thing is this part here, right, actually doesn't control whether it's over, under, or critically damped, because this is one real root, and multiplying a real root times a transfer function cannot make it over, under, or critically damped in and of itself. So I can kind of ignore it and just worry about this part. All right. So this is that wire. Right here. And I just drew this upside down. All right. So the feedback coefficient, beta, is just equal to 1. Right. Just to tell you where that came from. So let's just review how to find V out with a signal flow graph. So V out equals H of S times V in. And I'm going to drop the function of S because we're in the Laplace domain. This only works in the Laplace domain. But V out also equals its own self. It's a wire, right? Which gives a beta, right? That's 1. It's subtracted, but it's also multiplied by H, right? And so if we set beta equal to 1, okay. So let's first solve for V out by collecting the terms. Then solve for the transfer function. Now, I'm going to use QS here because we'll get confused about which transfer function we're talking about. Sometimes I'll call it H Opamp, right? Sometimes when you have a transfer function inside and you're finding a new transfer function, they'll call it Q of S, all right? And we get H 1 plus H. So now we're going to expand that, and we had 100, I believe it was 100. Yep, 100. Times 1 meg. Okay, so that's H, all right, 1 plus 100, 1 meg, S plus 10, S plus 100K, all right. So really, right, this is in the denominator, and so I can multiply it through. So when I multiply this by 1, I get the original poles, but then in this term, those pole numbers cancel out. So this is the important part, the denominator, right? And we already know what these poles were, right? It was 10, minus 10, and minus 100K. Those are real numbers, and they're different real numbers. So it was overdamped, right? But now we're adding something, and it's just a constant, right? But this will change the quadratic equation coefficients. But in order to do that, you have to multiply everything out. So now I'm just working on the denominator. So we have S squared plus 1 meg, right? And then I'm just going to do 100K plus 10S. All right. The reason why I do that is that this is so much bigger than that, it would be hard to kind of write out that number. Okay? And I see the chat, and I just want to finish a thought. Now, right, we have b squared minus 4 AC. Well, A is still 1, right? B is this term. So it's 100K plus 10 squared minus 4, A is still 1. But now notice C has changed to 1 meg times 101, right? And so now we could check that. If this is bigger than that, it'll be underdamped. If it's equal, critical. And if this is still bigger than this portion, then it will still be overdamped. Okay. Why do we have the constant? So I'm assuming, why did you add this constant here? Right. When we took that function here and added the feedback, right, we came up with this equation, right? When I multiplied the denominator of the transfer function by the denominator of the whole transfer function, right, this part was multiplied by 1, right? So I get S plus 10 Oh, okay, yeah. Okay, yeah, it's the result of the feedback loop. Very well summarized, Nick. So anyway, um, 100e to the 3 plus 10 squared, right? And then, yeah, if you're worried about it, we'll just subtract this from that and see what are you getting, right? And so this was greater than 0, overdamped. Okay, like all I really need to do is just, find that difference. I don't need to know what it is because I'm not actually, in this case, trying to find the root. I just need to know whether it's bigger, equal, or less, bigger than 1, equal, or bigger than 0, equal to 0, or less than 0.
Is A 1 in this case? Yeah, out of your quadratic formula.
Right, A is 1.
And the C is 1 meg.
No, the C.
Where did the
C equals 1 meg plus 100 meg. See, it changed. Before the feedback loop, it was 1 meg. After the feedback loop, you're adding it together. So I pulled out the meg.
Okay, I was just wondering where the times 10 came from.
Yeah, is that Mike?
Yeah.
I'm like,
Hey. Yeah, I was just wondering where the times 10 came from. You have 4 times 1 meg times 10.
well, that's 101.
Oh, so, okay. Gotcha. Okay, sorry about that. Thanks.
No, kind of important. So I'm glad you asked. So that's the, kind of the model, right? Now, sometime like, so this is like a question that's over, under, and critically damped, right? And the thing is in order for it to be over, under, or critically damped, I have to start with a transfer function with at least 2 poles to begin with. Otherwise, the question doesn't make sense, all right? But what we can also do is, while we're here, right, there's other questions, right, where I'll say, in what region does this act like this, right? Where, that's the transfer function right here. And then this is supposed to be a buffer, right? So what frequency range does this work at, right? And so I actually can tell, or I can look at the relationship right here, right? And so QS is the Opamp part. And if it's a buffer, right, we want QS equal to 1. So all we got to do is find out, when this term, right, is a lot less than that term, all right? And then we can determine that, all right? But before we get into that, are there any questions? Okay. Now, I do have a lot of case studies on the gain bandwidth and determining the range of a frequency range and things like that. But I wanted to do a quick example of a DF2 design. All right. Because we do have time to cover it a little more, even though by day, it doesn't merit a whole day, but I can do this. So anyway, we have a transfer function and it's a third order, right? And ds can be s cubed, or b3 can equal a3, or it can equal this. And this would be, if I had it for this, it'd be high pass, that'd be low pass, and that would be notch. once you design the denominator, all you have to, in the DF2, all you have to do is take the nodes out properly to make whatever filter you want. So with the RLC filter, right, it all depended, did you take the voltage across the resistor, the inductor, the capacitor, or the inductor and the capacitor, and then you could get the various band, low, high filters from there. Why is it DS? Because I was checking you guys to see if you noticed that I was screwing it up. Sorry, numerator. Okay, so Sebastian, when you say how can you tell if it is under overcritically damped, are you talking about the problem right now or the one that we just did? Or is that an old chat? Okay. All right. Let's just reiterate it though. Okay. This is the denominator, right? And that's what you use the quadratic equation for, right? And in this case, this is bigger than 0, so it's overdamped, right? I don't have to worry about the rest of the quadratic equation. I'm just worried about the part that will tell me whether I got repeated, different, or complex poles. So I'm going to answer Sebastian's question first. Yes, if it's less than 0, you get a negative number. Square root of a negative number is complex. And so you have a real number plus or minus a complex number. So you get complex poles. So DF1, right, as Nick is saying, it's more of a technique used in DSP where, yeah, you're using digital signals. And there's reasons that I don't want to get into here, but it can be a good technique for there. But here, it would use too many op amps. And so we're using DF2, except only the book calls it DF1 and DF2. If you really want to study the matter more, they're called state space filters. And other books just they kind of tell you, like, for this style of filter, they don't even mention the other one, okay? Yeah, state space. Even though we're using a transfer function and not the state space things. But yeah, when I first tried to teach this, and I'm trying to find information on DF2, they are both state space filters, yes. But if you were to look up state space filters, you're not going to see DF1, right? Op amps space, you're only going to see the way I'm showing you. And so I found that it was a distraction in class, so I don't even mention it anymore. Okay. But those are great questions. The very same question I had. Anyway, back to the numerator. So what I'm saying is if I switch out numerators, right, and all that really means is taking the voltage off of a particular node, I'm changing the filter. Oops, spoke too soon. I'm going to get into that, okay? So this is 6.28. This is 1.97 to the 9th, 3.1 times 10 to the 13th. And yeah, for a low pass filter with 0 dB gain, B3 equals A3. All right. Okay. So regardless of what the numerator is going to be, you actually design almost everything the same. And it's at the very end where you take V out, right? Or put it this way. This is like the structure in R's and C's. And up here is where you take V out. All right. So let's just do it. So it's a third order, right? This is an integrator-based technique. So we need 3 integrators. So again, I draw 3 integrators. And yeah, it's like I'm a little computer program following an algorithm. Because when I do that, I'm less likely to make a mistake. I'm drawing the op amps, oops, in between that node, right? And then I just, oops. Okay, 1, 2, 3 integrators. And I like to call these R1, R2, R3, C, 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 because I know that I'm going to make all those C's the same. Unless I can't do it, then I go back and change it, okay? But that's my first assumption. Oh, hold on a second. No, it's not. It's right there. Thanks for telling me. Okay. Yeah. They're all long days, I think, in engineering. Excuse me. So then what I do is I draw the summer. And then I fill in the parts that I know I'm going to need, however I'm going to do it. And I'm already making an assumption on the resistance. All right. Now, you guys are great, I got to tell you. So now I think I was talking to somebody today when they said, I start saying, and this one's negative and it goes this way, and this one's positive and it goes this way, and this one's negative and it goes that way. And while it's all very true, I know it might be a little bit, I might be saying it too fast, right? But if I'm going to just try to draw that original block diagram, right? Where you had a summer, there was an integrator, right? And then you had a constant and it was minus, right? All of these, and then if I had a second order, right? So here, yeah, I'm just adding everything. And in here, I'm somehow making it negative. So everything needs to be so Nick, your question's a little bit too deep for today. And the idea of why everything is a minus, I've kind of done that a few times. If we have time, I'll go over it, okay? But even today, here, right, I said that was negative. I start doing the math, right? V and H minus this thing. Then I collect the terms and then everything is positive, right? So if it was in fact negative, so if in fact the term was positive, this would become negative, and instead of e to the minus t, where things decay, you get e to the t, and things expand and they get out of control, okay? So, anyway, so we kind of have to take it right now for today that these are all going to be negative feedback, all right? Otherwise, it's not a filter, it's just something that explodes. So I want minus A1 here. Well, that's great because I get minus R1C S coming out of that node, right? So it's already minus. So I'm going to feed it back here on the positive side, because the plus times a minus is still the minus, right? Here, we actually get minus R1C, R2C, S squared, but it's positive because this transfer function was negative times this transfer function, which was negative, gives us a positive. Well, according to this, everything has to be brought in negative. I'm going to use another color and try to snake it through. So that means I have to bring it in on the inverting side. Okay. And in a similar fashion, I get this. Because this node is minus R1CS times minus 1 R2CS times, I gotta move the chat box, minus R3CS. Minus times minus is positive, times minus is negative. It's already negative. This gives me my S cubed. I get R1, R2, R3, okay? So I need to bring it in on this side. All right. Now, in this picture, everything was 1 over S. I'm a bit out of room here, but what I'm going to redraw it, but to just give you an idea of how I deal with the summer, is that I make R1 and C equal to 1 over R1C, right? I make that equal to A1, right? So it's really A1 over S. So then it's like minus 1, or in fact, it's minus A1 over S, which then I just add times 1. So I do that for all these nodes. I make the constants, the A1, 2, 3, I control them with these. So now on the summer, right, the gains are all just plus or minus 1. And so I have plus 1, I have another plus 1, another plus 1. So I have 3. And here I have 1 minus 1 gain. So I need to have, I need these 3, I can't get rid of them. So I need to have another minus 2, so I add a dummy, and then I add another dummy. Okay. Now, most people recognize that 100K, 200Ks in parallel is 50K. I leave it like this, not because I'm going to do it that way, but you can see what I'm doing, where 1, 2, 3, 1, 2, minus 1, minus 2, minus 3. All right. Now, I need to explain this business a little bit more. So we have the summer. We have 1 over S minus A1 plus. Okay. Well, then this becomes, we still have the summer, which is that op-amp circuit, but it's actually minus A1 over S. And then my feedback is plus 1. And then I just add it in that way. All right. Now, I set up the next series of resistance and capacitance pair so that I get this, because I'll get minus A1 over S times minus A2 over A1 over S. The A1s cancel out, right? And it's positive. So this becomes A2 over S. So when I put that back in the feedback, I got to multiply that by minus 1 before I bring it in. And then here, the transfer function would be A3, A2 minus S, right? So I multiply these all together. The A1s cancel out, the A2s cancel out. S times S times S, S cubed. Minus times minus times minus is minus. So it's already minus. So then I keep it positive and then and add it back in. So that's really what's going on here. All right. Now, while this is true, it's really easy to notice that this equals, right, A1 R2 C, right? If I plug that in there, right? And then it's easy to, it should be easy to see, no, yeah, that's right. And then we have a 2 So that effectively R1 equals one divided by A1. Where's that? C, right? And then R2 should equal A1 divided by A2 C. Right. And so if C equals 1 nanofarad, R1 is 16K, you know, roughly 32K, and 64 kiloohms. Okay. Okay. If you're not reading the chats, you should read the chats. So now, all right, let's try to draw a cleaner circuit now that I have my values. Right, third order circuit, 3 capacitors, right? 3 integrators. I see, I'm just finishing this up. Okay, so now, so here's the thing, this creates ds equals s squared plus, cubed. What about, what kind of filter, right? Yeah, Kevin, you're right. No. I got R1, R2, and R3 from this calculation setting capacitance to 1 nanofarad. Here are the design equations, right? But it's easier to manipulate them like this, right? And so then I just solve for each individual R. So I do have a lot of videos and case studies on just about every possible combination of that, all right? Oh, you're saying it should be 62? Let me double check. I don't know. I rounded it up to 64. Right. I was rounding things up, but I used Excel. Okay. Yeah. Meaning, oops. This I got 16K, or, you know, this was 31.8. And so I rounded that up. And then this was 6.35 times 10 to the fourth, right? And so I rounded that up, okay? Rather than round this one and then use it in my calculation and then use it in my calculation. I just calculated it and then rounded it from there. But yeah, okay, good question though. Oops. Yeah, so yeah, today you're seeing, you know, if I were to do a design, you're seeing exactly kind of how I did it, except the Excel file's on another computer because nobody seems to like my headphones when I use that to teach, and only my laptop has a decent mic. Okay. I'm just gonna sorry, I'm just saving something so that I can bring it over. So here we go. All right. So kind of gone over where things come from, but right now, this node here is the high pass node. And I can even call it that. Excuse me. And over here is the low pass node. And here is the band. And what I want to do is, so the cutoff frequency was 5,000 hertz. So let's go from 50 to, let's see how that works. Okay. So it's 0 dB. And when I go plus or minus the same distance and just click on it, right, it's right at the cutoff frequency, minus 3 dB, you're very close. Now, interestingly enough, you might say, wait, if it's a low pass filter, why is the phase plus 45? Well, I'll tell you, is that we have minus here times a minus, so it's plus times a minus. So in fact, we have to multiply all of this by -1 to get the true, to get a non-inverting function, okay? So now you can see that the phase is right. And this again, it's an Opamp, you know. Now, yeah, the high pass, right? It's right there. Starting to roll off due to the Opamp finite gain bandwidth. And then I can click on the band. It looks funny. Okay. And then to create the notch, something's not right. You just have to sum those two nodes. Oops. How do I sum those? I have to add these two nodes, but this node is inverting. So I need to uninvert it. So I bring it through the inverting part of the summer, right? I need to add the high pass. It's not inverted and I want to keep it not inverted. So then I added it on this side. Okay. And that should work. And if it doesn't, you know. So I got to look into that. Okay. Sometimes you got to change the constants, but I must be a little bit blind not to see my own mistake. All right. Because, yeah, there's one input, one input. Yep, I'm just going to have to look into that. Okay. Oh, sorry. A notch filter. So I'll answer both questions. So, right, you know, assuming that's frequency, that's low pass, right? Low pass, high pass, band pass, which you can even just do that, right? It gets the idea. And a notch is supposed to do that, okay? And what it's doing is it's just adding it somehow. Something that I was able to do before isn't quite working here today. So that's what it should look like. And this is just various orders. And so my thoughts were I was all right, so it looks like for a third order filter, okay. It's not perfect because all the resistor values changed, but basically, when you do a band stop filter that it doesn't have an even number of stages, you don't take it off the same point. Sorry for confusing you there, but on a on an exam or a homework, right? You're going to get H of S and you'll get some numerator and then a denominator, right? And you have to just so you can get everything designed, right? But you have got to say what V out is. So V out, or if I'm saying if H of S equaled B3, and then we had the denominator, then it's a low pass, right? And it comes out here. Although it's inverted, so you would have to put an inverter and call that V out. If I gave it to you S cubed, you'd have to call this out. So you have to get the right number of integrators, the feedbacks, and you have to label wherever out is, okay? No, I don't think I did. I could. So no, here's 16, 32, 64, 100, 100, 100, 100, 100, 100.
You should have another 100 on the negative side.
Huh?
On the op amp all the way to the right, the top
Yeah.
right, add another 100K resistor on the negative side.
Oh, is that what you were saying? I don't know, because I forgot. Still. So anyway, the problem is that these resistors here change with the filter characteristic I put in. So it's not quite going to work, but I'm giving you if you see something where you have, in this case, it would be B0 plus, okay, what I just drew with that summer.
I think he was referring to the, sorry.
No, I don't get it then.
The 16K and the 64K, or R7 and R8, you have 100Ks.
Everything should be 100.
And the notes, it's the R7 and R8 are 16 and 64.
Let's see. Yeah, that was a mistake. Which is why I use LTSpice to confirm what it is I'm doing. Okay? No, Nick, it's totally my fault. But whenever I do the solutions, right, I do them in LTSpice to make sure I don't mess it up myself. And so, yeah, you could do that because exams are open book, open note, open computer, just not open intelligence, except for the intelligence you bring. Okay. Anything else before we adjourn to EE 112? So no, LTSpice was correct, but I had it wrong for the notch. It turns out that the notch example doesn't quite work. So you want to follow whatever notes I've published. Yes, 2 homeworks are due because one was actually delayed to give you the flexibility. So, right, one of those homeworks, right, if I'd given the same amount of time, would have been due like Wednesday night. So I just pushed it all back for you. All right, guys. Take care and remember, look I think the people who come to office hours generally leave pretty happy. Not 100%, but okay. Take care.